You may have heard people say that light is both a wave and a particle. But that sentence is so familiar that we rarely stop to ask the more dangerous question: why did physicists ever become convinced that light had to be particle-like in the first place? So let us take this step by step. Because this is not a small correction inside physics. It is not a technical footnote. It is not some decorative twist added to make quantum mechanics sound strange and impressive. It is a deep wound in our ordinary intuition. After all, waves and particles are not just different labels. They are different ways of imagining reality itself. A wave spreads out. A particle stays localized. A wave can overlap with another wave and interfere. A particle seems to travel along a path, arriving in one place at one time. If something truly behaves like one, why should it ever need the language of the other? And yet, light forced physics into exactly that uncomfortable territory. So to answer this properly, we will need a strategy. First, we begin with the era when waves seem to have completely won. Then, we examine the first cracks in that picture. Next, we follow the specific experiments classical wave theory could not explain. After that, we derive the equations that made the particle picture unavoidable. And finally, we confront the modern answer. Light is not a tiny billiard ball, but something even stranger. Now, notice what kind of question we are really asking. We are not asking in a loose, popular science way. So, is light a particle? That version is too shallow. The real question is much more serious. What kind of evidence is strong enough to change the mind of physics? What experimental pressure becomes so great that a beautiful theory, a successful theory, a theory that once looked complete, must suddenly make room for something it never wanted? That is the heart of this story. Because for a long time, the wave picture of light did not look weak. It looked triumphant. It explained interference, where bright and dark bands appear when light overlaps with itself. It explained diffraction, where light bends and spreads when it passes through narrow openings. It explained polarization, a subtle property that fits naturally with transverse waves. And then, in the 19th century, James Clerk Maxwell fused electricity and magnetism into one of the greatest theoretical structures ever built, showing that light itself is an electromagnetic wave. At that point, the case seemed almost closed. Imagine being a physicist in that era. The wave theory is not some vague metaphor, is less than #0, 5# is greater than, it is supported by experiment. It is written in equations. It predicts a speed, and that speed matches the measured speed of light. This is not the feeling of a mystery waiting to be solved. This is the feeling of a theory that seems to have already found its place in nature. And that is exactly why the next chapter matters so much. Because when a weak idea fails, nobody is shocked. But when a powerful idea begins to crack, the entire structure of understanding trembles with it. To see how strange this became, let us slow down and think carefully about what we usually mean by a wave and what we usually mean by a particle. A wave is something spread out. It has crests and troughs. It carries energy across space, but not in the style of a tiny, solid object flying from one point to another. If you drop a pebble into a pond, the ripples move outward. The pattern lives across a region. The wave can reinforce another wave, or cancel it. It is naturally a story about extension, overlap, and pattern. A particle, by contrast, seems to be about individuality. A grain of sand, a bullet, a pebble. It may have a position, a path, a collision. It arrives here rather than there. It delivers energy in a more concentrated, localized way. Particles do not usually create interference fringes by spreading through space and overlapping with themselves. At least, not in classical intuition. So if you were told, before any quantum mechanics, to choose one picture for light, the wave picture would seem not merely plausible, but elegant. In many cases, undeniably correct. And yet, physics eventually found itself dragged into a deeply uncomfortable position. There were experiments in which light did not behave as though its energy was smeared out continuously across a wave. Instead, it behaved as though energy arrived in distinct chunks, almost like separate packets. That phrase matters. Distinct chunks. Because classical wave theory, in its most natural form, suggests that if you shine a weaker light for a longer time, energy should gradually accumulate. A system should be able to soak it up little by little, the way warmth from sunlight slowly heats a stone wall. But some experiments would later suggest something much harder, much sharper, much less forgiving. They seem to say that light does not always hand over its energy gradually. Sometimes it behaves as though the exchange comes in indivisible portions. People often say, almost casually, that light is both a wave and a particle is less than #0. 5# is greater than as though the story were just a small paradox to enjoy and move on from. But that misses how disruptive the transition really was. Physicists did not adopt particle-like light because it felt satisfying. They moved in that direction because the evidence left them no comfortable alternative. Science, at its best, is not the art of inventing the most satisfying picture. It is the discipline of accepting the picture that survives contact with reality. And this is what makes the story of light so compelling. Not because it is simple, but because it is honest. Let us pause for a moment and take stock. Up to this point, we have not yet proved that light is particle-like. We have done something more important. We have set the standard of proof. We have reminded ourselves that the wave theory was genuinely successful, deeply successful, and not easily replaced. That means any future argument for light quanta must do more than sound interesting. It must explain something that the wave picture truly cannot. That is the burden of proof. And in a way, that burden is what makes this one of the great detective stories in all of physics. The mystery is not, what strange thing can quantum mechanics say? The mystery is, what did the world do that left physicists no graceful way to hold on to their old picture? Because make no mistake, they resisted. They resisted because the wave picture explained too much to abandon lightly. They resisted because interference and diffraction were not optional details. They were central facts. They resisted because James Clerk Maxwell's theory was among the crowning achievements of 19th century science. To say that light might also need a particle-like description was not to add a small refinement. It was to open a door to a reality more complicated than the old categories could comfortably hold. And that is why this question should not have survived. By all appearances, it should have been settled. Light should have remained a wave. Full stop. The textbooks of the late 19th century could almost have ended there, satisfied. But nature did not cooperate. The closer physicists looked at how light exchanged energy with matter, the less complete the old certainty began to feel. The wave picture still worked magnificently in some domains, but in others, something slipped through its fingers. What slipped through exactly is the journey we are about to take. We will watch classical confidence rise to its peak. We will watch it begin to fracture. We will meet the crisis of blackbody radiation is less than #0. 5# is greater than where energy refused to behave continuously. We will step into Albert Einstein's radical leap, where light itself was treated as coming in quanta. We will follow the photoelectric effect, where frequency seemed to matter more than intensity in a way that classical waves struggled to explain. We will move into Compton scattering, where light appears to carry momentum like a particle in collision. And then, when the old words begin to fail completely, we will arrive at the modern view, where neither wave nor particle is the final truth, but each reveals part of a deeper quantum structure. So before we move on, keep one thought in mind. This story is not about replacing one simple picture with another simple picture. It is about understanding why physics was forced to outgrow simplicity itself. Because when we say that light is particle-like, we are not saying that physicists became bored with waves and wanted something more dramatic. We are saying that a chain of evidence, built slowly and carefully, made it impossible to remain fully classical. The belief was not declared. It was earned. Light is both a wave and a particle. Stop sounding like a slogan. It begins to sound like the mark left behind by a long argument between theory and experiment. So now we are ready to ask the first real historical question. If waves explained light so beautifully, if interference and diffraction and James Clerk Maxwell's equations had made the wave picture seem almost irresistible, why did anyone become dissatisfied with it at all? If we want to understand why the return of light as particle was so surprising, then we have to do something very important first. We have to be fair to the wave theory. We have to resist the temptation to tell this story as though physicists were somehow mistaken, waiting for quantum mechanics to correct them. That is not what happened. Before the 20th century, there were powerful, elegant, deeply convincing reasons to believe that light was a wave. Not a vague suspicion, not a placeholder. A serious, successful, mathematically rich description of nature. And to feel the force of that older confidence, we should begin with a rivalry that shaped the early history of optics. For a long time, there were two broad ways of imagining light. One was associated with Isaac Newton, who pictured light as made of tiny corpuscles, little projectiles streaming outward from luminous bodies. This idea had obvious appeal. It made light seem direct, clean, almost mechanical. A source emits something, that something travels. It enters the eye. Vision happens. There is a satisfying simplicity to that story, and Newton's authority gave it enormous weight. But another picture, developed by Christian Huygens, suggested that light behaved more like a wave spreading through space, with every point on a wavefront acting as the source of further ripples. That picture was less intuitive to some minds, but it possessed a quiet strength. It could explain reflection and refraction in a way that felt less like a stream of pellets and more like an evolving pattern. For a while, the contest was not decisively settled. That is worth remembering. Science often lives for long periods in these uncertain states, where multiple pictures seem plausible, and where the winner is not chosen by taste, but by what nature eventually allows. Then came Thomas Young. Young's double-slit experiment did not merely add another curious optical effect to a growing list. It changed the balance of the entire debate. The setup was disarmingly simple. Light from one source was allowed to pass through two narrow openings, and then fall onto a distant screen. If light were just a spray of tiny particles moving in straight lines, you might expect two bright regions, perhaps softened a little by imperfection, but still essentially two illuminated patches. Instead, what appeared was a series of bright and dark bands, a striped pattern. Some regions were strongly lit, others unexpectedly dim, and some nearly dark. Young interpreted this as interference. The light from the two openings spread out, overlapped, and in some places reinforced itself, while in others it cancelled itself. That is the language of waves. It is the behavior of overlapping ripples on water, not the behavior of ordinary pellets in flight. This mattered enormously, because once interference is real, the particle story loses its old ease. A particle can hit here or there. It can bounce. It can scatter. But the idea that darkness can be produced not by absence, but by cancellation, belongs naturally to waves. It suggests that light is not simply arriving in isolated little bits, each minding its own path. It suggests that light has phase, spread, rhythm. It suggests that light can combine with itself. And Young was not the end of it. He was the first clear breach in the wall. Augustin Jean Fresnel came next, and he did what great theorists often do. he took an arresting experimental clue and turned it into a whole architecture of explanation. He pushed wave optics much further, is less than #0. 5# is greater than, especially in the study of diffraction, the strange spreading and bending of light around edges and through narrow openings. Diffraction had been noticed earlier, but Fresnel gave it structure. He showed that if light is wave-like, then these fringes, soft boundaries, and delicate shadow patterns are not awkward complications. They are exactly what one should expect. And this is the point where the case for waves stopped looking like a philosophical preference and started looking like a scientific victory. Because light was no longer wave-like in just one special experiment. It behaved like a wave across a whole family of effects. Interference, diffraction, polarization. One by one, phenomena that seemed awkward under a corpuscular picture began to sit naturally inside wave theory. The evidence was beginning to cohere. At this stage in history, the wave theory was not surviving by habit. It was earning trust. It explained patterns that particle-like pictures struggled to handle cleanly. It connected separate optical effects under one common language. And that matters because in science, a theory becomes powerful not only when it explains one thing, but when it explains many things at once. Still, even here, one could imagine a critic saying, "All right, perhaps light behaves as if it were a wave in these optical settings. But what kind of wave is it? A wave in what medium? A vibration of what exactly?" That question hung in the air for much of the 19th century. And then Maxwell arrived. James Clerk Maxwell's achievement was so profound that it is difficult to overstate. He took the scattered laws of electricity and magnetism and brought them together into a unified framework. What emerged from his equations was not merely a bookkeeping system for electrical and magnetic effects. Something much deeper appeared. In empty space, a changing electric field can give rise to a magnetic field, and a changing magnetic field can give rise to an electric field. In other words, these two fields can sustain one another, handing the disturbance forward through space like two partners moving in perfect step. When Maxwell followed the logic of that structure, he found that these coupled disturbances should travel as waves. And not just any waves. The speed that fell out of the theory matched the known speed of light. That was the thunderclap. Light was no longer simply behaving like a wave in a few carefully arranged experiments. Maxwell's theory suggested that light is, in its very nature, an electromagnetic wave is less than #0. 5# is greater than a propagating pattern of electric and magnetic fields moving through space. Try to feel what that meant to a physicist of the time. It was not merely that wave theory explained some laboratory patterns. It was that light itself suddenly seemed to belong to a much grander structure. Light was no longer just something that waves. It was identified with electromagnetic radiation. It became part of a unified description of nature. The equations did not have to be forced to include light as an afterthought. Light emerged from them as though it had been waiting there all along. This is one of those rare moments in physics when theory does something almost astonishing. It does not just tidy up known facts. It reveals a deep identity between things once treated as separate. Electricity, magnetism, and light were understood as aspects of one continuous framework. That kind of synthesis leaves a powerful impression. It makes a theory feel almost inevitable. Not because Newton had become unimportant. Not because particles were suddenly absurd. But because the wave account had become too successful, too elegant, too mathematically fertile to ignore. By the late 19th century, many physicists felt that the great battle had essentially been decided. The question, "What is light?" seemed to have an answer. Light is an electromagnetic wave. Full stop. That is the mood we must carry forward. Because if we forget how complete that victory felt, then the coming crisis loses its force. The shock of the quantum era depends on this earlier certainty. The return of particle-like behavior was not dramatic because physicists had no idea what light was. It was dramatic because they believed they already did. Light as a wave was not a weak guess. It was backed by Young's interference, Fresnel's diffraction, and Maxwell's equations. It explained why light could spread, overlap, bend, and organize itself into patterns of brightness and darkness. It sat inside one of the great theoretical triumphs of classical physics. Any future argument for particle-like light would have to overcome all of that. It would have to challenge not a fragile opinion, but a mature and deeply successful worldview. The wave picture had won because it deserved to win. It had evidence. It had predictive power. It had beauty. And perhaps most importantly, it had unity. Light no longer seemed like an isolated puzzle. It seemed woven into the electromagnetic fabric of the world. So now, the real tension sharpens. If the wave picture was this successful, if it was this deeply grounded, is less than #0. 5# is greater than if it seemed to explain light so beautifully. What kind of evidence could possibly force physicists to reopen the case? You may have heard people say that quantum theory began when physicists discovered that nature is strange. But that is not quite how it happened. The truth is more unsettling, and in some ways more beautiful. Quantum theory did not begin because physicists went looking for mystery. It began because classical physics, after centuries of triumph, walked straight into a calculation so absurd that it seemed to predict an impossible universe. To understand that crack, we need a strategy. First, we need to understand what the blackbody problem actually was and why it seemed so innocent at first. Then, we need to see how classical reasoning tried to solve it and why that solution exploded at the high-frequency end of the spectrum. Next, we follow Max Planck's remarkable move in 1900, when he introduced the idea that energy exchange might come in discrete amounts. After that, we ask the crucial historical question: did Planck believe he had discovered something physically real, or had he merely invented a clever mathematical trick? And finally, we prepare the deeper question. So let us begin with the object itself. A blackbody, despite the name, is not really about color. It is an idealized object, one that absorbs all incoming radiation perfectly, no matter the frequency, no matter the angle. Nothing is reflected away. Nothing escapes that is not part of its own thermal glow. If you heat such an object, it radiates, and the light it emits depends only on its temperature, not on its shape, not on its chemical identity, not on whether it is iron, clay, or carbon. Just temperature. That made it an extraordinarily clean problem. Physicists could build approximate blackbodies in the laboratory by using a cavity, a box with a tiny hole. Light entering that hole would bounce around inside, scattering so many times that it was overwhelmingly likely to be absorbed. And the little opening would then act as an almost perfect emitter. In effect, the hole itself became a window into pure thermal radiation. This was not a side issue in physics. It was central. Here was a chance to understand how matter and radiation share energy. Here was a chance to derive, from first principles, the color and intensity of a glowing object. Why does a hot stove glow red before it glows white? Why does increasing temperature not merely make something brighter, but also shift where most of its radiation is concentrated? These were not decorative curiosities. Is less than #0, 5# is greater than. They were clues about the deep bookkeeping of energy itself. And at first, classical physics approached this problem with confidence. Why not? Classical physics had conquered mechanics. It had unified electricity and magnetism. It had explained waves, heat, and gases with astonishing success. So the expectation was simple. This, too, would yield. The reasoning went something like this. Inside the cavity, electromagnetic radiation can exist in many possible modes, many possible standing wave patterns, each with its own frequency. Classical, statistical physics then brings in a powerful idea. In thermal equilibrium, energy should be shared fairly among the available modes. Each mode gets its little portion. No favoritism. No special treatment. That sounds almost democratic. And for many problems in 19th century physics, it worked beautifully. But here was the disaster. The number of available modes rises rapidly as frequency rises. The higher you go in frequency, the more and more ways the cavity can support electromagnetic oscillations. So if classical physics insists that each of these modes receives its ordinary share of thermal energy, then the high-frequency region becomes a monster. There are simply too many modes there. More and more slots, each demanding its own portion of energy. And so the total radiated energy begins to pile up catastrophically. The classical prediction, later associated with Rayleigh and Jeans, behaved reasonably enough at low frequencies. But as you moved toward higher and higher frequencies, toward shorter and shorter wavelengths, it rose without mercy. It did not level off. It did not turn over. It did not politely fail by a small amount. It marched toward infinity. That is the ultraviolet catastrophe. The name sounds dramatic because the result truly was dramatic. According to the classical picture, a hot object should dump an unlimited amount of energy into the high-frequency end of the spectrum. A warm oven, a piece of heated metal, a glowing cavity, all should radiate absurdly intense ultraviolet and beyond, with no upper restraint. In other words, ordinary heated matter should pour out infinite energy. Nature, of course, does no such thing. Real measurements showed something much calmer, much more graceful. As frequency increased, the emitted radiation rose for a while, reached a peak, and then fell away. There was structure. There was restraint. There was no catastrophic flood of ultraviolet energy. The observed spectrum had a hump, not an explosion. This mismatch was devastating because it was not hiding in some remote corner of theory. It was right there in a basic thermal phenomenon. A heated cavity in equilibrium, one of the cleanest objects imaginable, was refusing to obey classical expectations. Until now, the wave theory of light had been accumulating victory after victory. Interference, diffraction, polarization, Maxwell's synthesis, all of it pointed toward continuity. Light as an electromagnetic wave seemed almost complete. But the blackbody problem did not attack the wave description of propagation. It attacked something more subtle, the assumption that electromagnetic energy could be exchanged continuously, without limit, in arbitrarily small amounts. That is an important distinction. The blackbody crisis was not yet proof that light itself was made of particles. It was, instead, the first serious warning that somewhere in the interaction between matter and radiation, continuity was breaking down. Enter Max Planck. Planck was not trying to overthrow classical physics. He was trying to save it. That matters. He was not a revolutionary in temperament. He did not set out to declare that nature comes in discrete packets. He was trying, as many great physicists have done, to rescue the data with the smallest possible wound to the old world view. What he found was extraordinary. To reproduce the observed blackbody spectrum, Planck made an assumption that at first seemed almost artificial. He imagined that the microscopic oscillators in the walls of the cavity, the little charge systems exchanging energy with a radiation field, were not free to emit or absorb any arbitrary amount of energy. Instead, they could do so only in discrete steps. Not a smooth ramp, not a continuous pour, but in little bundles, each bundle tied to the frequency involved. The higher the frequency, the larger the size of each bundle. That idea can be expressed in a compact formula, but the heart of it is simple enough to say in words. The energy available in an exchange is built from whole units, and the size of one unit is set by a new constant of nature multiplied by the frequency. The constant is now called Planck's constant. The frequency tells you how rapidly the oscillation occurs. Temperature measures the thermal agitation of the system, and Boltzmann's constant acts as a bridge between microscopic energy and macroscopic temperature. But the main conceptual shock is this: is less than #0. 5 is greater than energy is no longer allowed to vary completely continuously in the interaction. That single move changed everything. Why did it help? Because it made high-frequency modes expensive. In the classical picture, every mode gets its share almost casually. In Planck's picture, the high-frequency modes demand larger energy chunks to be excited at all. And, at a given temperature, those large chunks are harder to come by. So instead of the ultraviolet end filling up without limit, it becomes increasingly suppressed. The spectrum rises, peaks, and then declines. Exactly the kind of behavior the measurements were showing. This is one of the most profound moments in the history of science, because the fix is at once minimal and radical. Minimal, because Planck was still trying to preserve as much classical structure as possible. Radical, because the move he made introduced discreteness, where continuity had long been assumed. Classical physics distributed energy too generously among too many high-frequency modes, and the result was absurd. Planck repaired the spectrum by saying that energy exchange does not happen in a perfectly continuous flow. It happens in steps. The quantum idea entered physics not as a grand philosophical declaration, but as a rescue operation. When Planck introduced this quantization rule, did he think he had discovered that nature itself is fundamentally granular? Or did he think he had found a mathematical device, a formal trick, a clever counting rule that happened to fit the data? The historical answer is subtle. Planck himself did not immediately behave like a man announcing the death of continuity. He was cautious, deeply cautious. He had introduced the assumption because it worked, because it gave the correct spectrum, because it rescued physics from catastrophe. But whether those discrete energy elements were physically real or merely part of the bookkeeping remained unclear. And this uncertainty is essential to the drama. Because if Planck had boldly declared, right then and there, that light itself comes in packets, the narrative would be simpler, but less true. The actual history is more hesitant. The first quantum idea entered the stage wearing the clothes of a technical patch. It solved the immediate problem, It saved the measured spectrum. But it did not yet tell physicists what kind of reality they were supposed to imagine behind it. Was the discreteness in matter? Was it in radiation? Was it only in emission and absorption? Or was it somehow a temporary scaffold is less than #0? 5# is greater than useful for calculation, but not to be taken literally? These questions would not remain quiet for long. Because once Planck's rule was on the table, it changed the atmosphere of physics. It did not yet prove that light was particle-like, but it made one thing impossible to ignore. The old dream of perfectly continuous electromagnetic energy exchange had taken a serious blow. The smooth classical picture had survived many tests, but here was a place where it seemed to run past reality and fall into nonsense. And whenever a theory predicts infinity, where nature gives finiteness, physicists pay attention. So this is where the first cracks appear. Not yet in the idea that light propagates as a wave. That picture still stands strong. Not yet in the full birth of the photon. That word has not earned its place quite yet. But in the older assumption that electromagnetic energy can always be traded continuously, in any amount, at any scale. There, for the first time, classical confidence begins to hesitate. And that hesitation opens the next question, the dangerous one. If Planck quantized the exchange of energy, did that mean light itself came in packets, or only that matter interacted with it that way? There are moments in the history of physics when a scientist solves a problem. And then there are rarer moments, far more unsettling ones, when a scientist solves a problem by quietly suggesting that the world may not be made the way everyone thought it was. This is one of those moments, because Planck had introduced the first crack in continuity almost reluctantly, as though he were patching a leak in classical physics. But in 1905, Albert Einstein did something much more dangerous. He looked at Planck's idea and asked a question that many others were not yet willing to ask. What if the discreteness does not belong only to the matter that emits light? What if, in some circumstances, the light itself behaves as though it comes in separate packets? By the time Einstein entered this story, Planck had already done something extraordinary. He had shown that the blackbody spectrum could be understood if energy exchange came in steps rather than as a perfectly continuous flow. But there was still an escape route available to classical intuition. One could still imagine that the radiation field itself remained a smooth wave, while only the tiny oscillators inside matter were restricted in how they emitted or absorbed energy. In other words, perhaps the granularity belonged to the atoms or charges in the walls of the cavity, not to the light traveling through space. That was the safer interpretation. It preserved as much of 19th century physics as possible. Light could remain an electromagnetic wave in the Maxwellian sense, spreading continuously through space, interfering with itself, bending around edges, producing the beautiful optical effects that had made wave theory so convincing. The quantum restriction, under this more conservative reading, would belong only to the handshake between matter and radiation. Einstein was not satisfied with that. In 1905, in one of the most astonishing papers ever written, he proposed that under certain conditions, the best way to think about light was not as a continuously spread out wave, but as though its energy were concentrated into distinct, localized quanta, not just at the source, not just at the detector, in the light itself, or at least in its physically relevant behavior. That was the leap, and it is hard to exaggerate how bold it was, because this was not a minor adjustment to the edge of an accepted theory. This was not the kind of move where you change a coefficient, improve an approximation, or rescue a failed prediction while leaving the rest of the worldview intact. Einstein was reaching into the heart of classical continuity and pulling at one of its deepest threads. He was saying, in effect, that the electromagnetic field, which Maxwell had described so triumphantly as a wave, sometimes behaves as if it comes in individual energy packets. Later, those packets would be called photons. But in 1905, the language was still raw and unsettling. Einstein spoke of light quanta. The phrase itself carried a kind of shock. It felt unfinished, provocative, slightly improper. It sounded like a violation of the smooth elegance that classical electrodynamics had achieved. And that is exactly why so many physicists resisted it. To see why the resistance was so fierce, we have to remember what the wave theory of light had already accomplished. It explained interference, where overlapping beams could produce bright and dark bands. It explained diffraction, where light spread and bent through narrow openings. It fit naturally with polarization. And Maxwell's theory had not merely supported the wave picture, it had elevated it. Light was no longer just wave-like by analogy. It had become part of the electromagnetic structure of nature itself. So Einstein's proposal seemed, at first glance, almost like a retreat into the past. If light comes in packets, then what becomes of interference? What becomes of diffraction? What becomes of the idea that electric and magnetic disturbances propagate smoothly through space? To many physicists, the light quantum sounded like a return to Newtonian corpuscles dressed up in new language. It seemed to threaten the hard-won achievements of wave optics. This is what makes Einstein's step so courageous. He was not moving in the direction of comfort. He was moving toward deeper conflict. And yet he had a reason. He was not proposing light quanta because he disliked Maxwell. He was not trying to erase the successes of wave theory. He was responding to specific thermodynamic and statistical clues that suggested the classical field picture might not tell the whole story in every circumstance. In certain regimes, especially when light exchanged energy with matter, it behaved as though it were not infinitely divisible in practice. It behaved as though nature insisted on transactions in finite units. Here is the heart of Einstein's claim, expressed without letting the equation dominate the story. Each quantum of light carries an amount of energy set by its frequency. That means frequency is no longer just a descriptive feature of a wave, like saying one vibration is quicker than another. It becomes the price tag attached to an individual quantum. The higher the frequency, the more energetic each unit of light is. That was a revolutionary shift in meaning. In classical wave language, one often thinks about intensity as the main marker of how much light there is. A brighter wave seems like a larger wave, a stronger disturbance, more energy spread through the field. Einstein did not deny that intensity matters, but he reframed the question. Intensity could now be understood, in a quantum picture, as telling you something like how many quanta are present. Frequency, by contrast, tells you how much energy each one carries. This is a very different way of slicing reality. Imagine two kinds of rain. In one case, a storm becomes more intense because there are more droplets per second. In another, the droplets themselves become heavier. Classical intuition tended to think of light mostly in the first way. More intensity meant more energetic wave activity. Einstein's quantum view introduced something closer to the second distinction. Two beams can differ not only in how much light they contain overall, but in how costly each individual quantum is. Low-frequency light is made of relatively cheap packets. High-frequency light is made of expensive ones. And once you say that clearly, something remarkable happens. A whole class of strange experimental facts begins to look less strange. But at this point in the story, Einstein still stood in a lonely position. His proposal was daring precisely because it cut across the grain of the best established theory of light. Many physicists could tolerate Planck's quantization as a formal trick attached to matter. Fewer were willing to imagine that the beam itself, traveling through empty space, might require a description in terms of discrete quanta. Planck had restricted the way energy is exchanged. Einstein went further and suggested that light itself behaves, in some phenomena, as though it is made of energy packets. That did not yet erase the wave picture, but it did wound the idea that continuity was always fundamental, and because wave theory had been so successful, this move felt almost outrageous. Later, Einstein would become publicly associated, above all, with relativity, with the speed of light, space and time, and the deep architecture of the universe. But the explanation that most directly earned him the Nobel Prize was not relativity. It was his work on the photoelectric effect, which treated light in this quantum way. That is a beautiful irony in the history of science. The world remembers Einstein for bending space-time, but the committee recognized him for helping crack open the quantum. And still, we should be careful not to tell the story too neatly. Einstein was not declaring that light is simply a little bullet, a tiny bead, a miniature classical object flying through space in the ordinary sense. That misunderstanding comes later, and it causes endless confusion. What he was really doing was far subtler. He was saying that there are processes in which the energy of light behaves as though it is concentrated into finite, countable quanta, with each quantum tied to the frequency of the radiation. Later still, another relation would show that these quanta also carry momentum in a way linked to wavelength, reinforcing their particle-like character even further. But in 1905, the energy relation was already enough to plant dynamite beneath the old continuity. And notice how deep the challenge really was. Classical physics had grown up with the assumption that fields are smooth. Waves can become weaker or stronger by arbitrary amounts. Energy can be spread continuously. There is no smallest allowed piece of a wave. You can always imagine cutting the disturbance smaller. Einstein's light quantum says, not so fast. At least in the way light gives energy to matter, nature may refuse that endless divisibility. There may be a minimum transactional unit. This is why the idea felt so dangerous. It was not just a statement about optics. It was an attack on a habit of mind. It challenged the old faith that the world, at its most fundamental level, must always allow smooth gradations. It suggested that continuity, so elegant in equations, might fail in the actual commerce of energy. For many physicists, this was simply too much. If you accept light quanta too quickly, do you not destroy interference? If light is made of packets, how can those packets produce the graceful striped patterns that waves produce so naturally? If Maxwell's theory describes light as an electromagnetic wave, do light quanta mean Maxwell was wrong? These were not foolish objections. They were serious. They were exactly the right objections. Because any successful quantum account of light would eventually have to explain not only why light sometimes behaves as if it comes in packets, but also why it so powerfully behaves like a wave in propagation and interference. That full reconciliation would take time. For now, what matters is this: Einstein was willing to trust a new line of reasoning, even before the old categories had been fully repaired. That is often how revolutions begin. A theory does not arrive fully polished, with every tension resolved. It enters history, jagged, incomplete, offensive to common sense, but pushed forward by evidence that refuses to go away. And that is exactly where we now stand in the story. The first crack in continuity came from blackbody radiation. But that alone did not force physicists to say that light itself came in packets. Einstein took that additional step. He made the dangerous leap from quantized exchange to light quanta. And once he made it, physics could no longer remain comfortably classical. Because now the question was no longer abstract. Now the question became experimental. What phenomenon could possibly make such a radical claim worth taking seriously? What observation was sharp enough, stubborn enough, embarrassing enough to the classical wave picture that Einstein felt justified in saying the light itself behaves as though it comes in separate packets? That is where we go next. There are some moments in physics when a theory begins to fail gently. It misses a detail. It predicts the right trend, but not the right number. It bends a little under pressure, but does not break. And then there are rarer moments when an experiment looks directly at a successful theory and says, in effect, no, not here, not this time, not in the way you think. The photoelectric effect was one of those moments, because by the early 20th century, the wave theory of light was not a weak idea waiting to be replaced. It was one of the crowning achievements of physics. And yet, when light was shone onto certain metals, the response of nature did not look like the slow, continuous transfer of energy one would expect from a classical wave. It looked abrupt. It looked selective. It looked as though light were delivering its energy in counted parcels. Let us begin with the apparatus. Imagine a clean metal surface inside an evacuated tube. You shine light on that surface. If the conditions are right, electrons are knocked free from the metal and begin moving across the tube, where they can be collected and measured as an electric current. This already tells us something remarkable. Light is not merely warming the material in some vague general sense. It is causing individual charged particles to escape. Now, add one more ingredient. Suppose you place a voltage across the tube that tries to pull those emitted electrons back, opposing their motion. If this reverse voltage is made strong enough, even the fastest emitted electrons can no longer reach the collector. The current drops to zero. That particular voltage, the one just sufficient to stop the most energetic electrons, becomes a direct way of measuring how much kinetic energy they had when they left the metal. This is a beautifully sharp setup. You shine light in, electrons come out. You measure both how many come out and how energetic the fastest ones are. It is an experiment about energy transfer, and that is exactly why it became such a crisis point. Because the classical wave picture seems, at first glance, to offer a reasonable expectation. If light is a wave, then its energy is spread through the wave continuously. A more intense beam should carry more energy. So if you make the beam brighter, you might expect the electrons in the metal to absorb more energy and eventually escape more energetically. If the beam is dim, perhaps they should still escape, but maybe only after waiting a little while, gradually soaking up enough energy from the incoming wave. That sounds sensible. Nature did not cooperate. The first shocking result was the existence of a threshold frequency. Below a certain frequency, no electrons are emitted at all. Not fewer, not slower, none. You can brighten the light as much as you like within that low frequency range, and still nothing happens. The metal remains silent. But once the frequency rises above a certain threshold, electrons appear. This was already a severe problem for the classical wave picture, because if energy were arriving as a continuous wave, one might imagine that enough intensity should eventually free electrons, regardless of frequency. A brighter beam should mean more energy delivered. Perhaps the electrons would need more time. Perhaps the process would be inefficient. But why should there be a hard lower cutoff in frequency itself? And yet there was. That meant the color of the light, or more precisely its frequency, mattered in a decisive way that intensity alone could not replace. The second result deepened the crisis. When the frequency is above threshold, increasing the intensity of the light increases the number of emitted electrons, which means the current rises. More electrons are being liberated. But the maximum kinetic energy of the emitted electrons does not rise simply because the beam is brighter. To increase the energy of the fastest electrons, you must increase the frequency. This is a very strange combination if you are thinking classically. Brightness affects how many electrons come out. Frequency affects how energetic they are. The wave picture, in its ordinary form, would have preferred intensity to play the starring role in energy delivery. After all, a stronger wave should carry more energy. But the experiment was saying something more subtle and far more rigid. The important variable for the energy of an individual emitted electron is not how bright the beam is overall, but the frequency of the light. Then came the third result, perhaps the most psychologically damaging of all. The electrons are emitted almost immediately. There is no long wait while they gradually accumulate energy from a weak incoming wave. If the frequency is high enough, the emission begins essentially at once, even when the intensity is low. That is deeply uncomfortable for a classical picture in which energy is spread out smoothly over the wavefront and must somehow be gathered little by an electron before escape becomes possible. This is the point where Einstein's dangerous leap suddenly becomes not just provocative, but useful. His idea was simple in structure and revolutionary in meaning. He proposed that light does not always hand over energy as a continuously spread wave. Instead, in the photoelectric effect, it behaves as though it arrives in discrete quanta. One electron interacts with one quantum of light. If that quantum carries enough energy, the electron can escape. If it does not, then no amount of spreading that insufficient energy smoothly over time will save the process. That last point is everything. In Einstein's picture, the energy of a light quantum is set by the frequency. Higher frequency means a larger energy packet. Lower frequency means a smaller one. So, if the packet is too small to pay the energy cost required to liberate an electron from the metal, then the process simply cannot happen. And that energy cost has a name: the work function. The work function is the minimum energy needed to pull an electron out of a particular metal. You can think of it as the binding cost, the escape fee. The electron is not free to leave just because light arrives. First, the metal must be paid. Only what remains after that payment can appear as the kinetic energy of the emitted electron. This is where the energy balance becomes beautifully clean. One incoming quantum brings a fixed amount of energy, determined by the light's frequency. A certain portion of that energy is spent overcoming the binding of the electron inside the metal. Whatever is left becomes the motion of the emitted electron. So the maximum kinetic energy is simply the incoming quantum's energy minus the work function. That is Einstein's central relation for the photoelectric effect. Notice how much it explains at once. Why is there a threshold frequency? Because below that threshold, each quantum is too weak. It cannot pay the escape fee. No electron gets out. Why does increasing intensity increase the current, but not the maximum electron energy? Because increasing intensity means sending more quanta, not making each one more energetic. More quanta means more opportunities to free electrons. So more electrons are emitted, but the energy of each individual quantum is still determined by frequency. So the maximum kinetic energy of the emitted electrons stays tied to the frequency, not the brightness. Why is the emission almost immediate? Because the electron does not need to wait and slowly gather scraps of energy from a broad continuous wave. In the quantum picture, the relevant transaction happens in one shot. One quantum arrives. One electron receives its energy. If the amount is enough, the electron escapes at once. The classical wave picture would naturally expect energy delivery to build up gradually and to depend strongly on intensity. the photoelectric effect says otherwise. It says the decisive variable for emission energy is frequency, and Einstein's light quantum picture explains that with one compact energy balance idea, each electron gets energy in a single package, and the size of that package is set by frequency. Now let us go one layer deeper, because this is where the experiment becomes not just conceptually striking, but quantitatively precise. The stopping voltage tells us how much kinetic energy the fastest emitted electrons had. Why? Because if you raise the reverse voltage until even the most energetic electrons are just barely unable to reach the collector, then the electrical work needed to stop them matches their initial kinetic energy. In other words, the stopping voltage becomes a direct measure of the electron's maximum kinetic energy. So now, we can connect the experiment to Einstein's energy balance. The incoming light quantum brings an amount of energy determined by the frequency. The metal takes its required share, the work function. The remainder appears as the electron's maximum kinetic energy. And that same kinetic energy is what the stopping voltage measures. So the stopping voltage must increase in a simple linear way as the frequency increases. That prediction is extremely important. It does not merely say that frequency matters. It says frequency matters in a very specific, orderly, measurable way. If you plot the stopping voltage against the frequency of the incoming light, Einstein's model predicts a straight line. The slope of that line is tied to a universal constant of nature, and the point where the line crosses the frequency axis reveals the threshold frequency, the minimum frequency needed to eject electrons at all. This is not hand-waving. It is not philosophical decoration. It is a clean experimental signature. And it is worth noticing how elegant the logic is. Brightness controls how many quanta arrive. Frequency controls how much energy each one carries. That simple separation explains the otherwise puzzling split between electron number and electron energy. Classical theory had no comparably natural way to do this. It might try to argue that the metal has some complicated internal resonance, or that energy accumulates irregularly, or that the surface behaves in a strange non-linear way. But these would be patches, not a clean organizing principle. Einstein's picture, by contrast, makes the whole experiment feel almost inevitable. This is why the photoelectric effect became such a turning point. Not because it instantly convinced everyone. It did not. Not because it destroyed wave theory in general. It did not. But because it isolated a situation in which the classical wave picture behaved awkwardly, while the light quantum picture behaved with sharp confidence. The experiment was not asking how light spreads through space in general. It was asking how light transfers energy to matter in a very specific encounter. And in that encounter, the evidence seemed to favor discreteness. Historically, this mattered enormously. Einstein's explanation of the photoelectric effect later became the most famous reason he was awarded the Nobel Prize. That fact is worth lingering on for a moment, because it reveals what the physics community eventually came to recognize. This was not a side note in the birth of quantum theory. It was one of the central demonstrations that the old continuous picture could not be the whole truth. And yet, at the same time, the situation was still not fully settled, because a skeptic could still say something like this: perhaps the discreteness belongs not to light itself, but to the electrons in matter. Perhaps the metal responds to a wave of light in some strange quantized way, while the light remains fundamentally continuous. Perhaps the photoelectric effect reveals an oddity of matter, not a deep truth about radiation. That objection mattered. It meant that even after the photoelectric effect, some room remained for resistance. One could admit that Einstein's formula worked, admire its precision, and still hesitate to say that light itself, out in empty space, truly comes in packets. And that is what makes the next step so important, because the photoelectric effect strongly suggested that light delivers energy in discrete amounts. But was that enough to convince everyone? Or could the effect still be dismissed as a strange property of matter rather than of light itself? There is a particular kind of drama that science produces better than almost any other human activity. It is not the drama of a person falling in love with an idea and defending it to the end. It is the opposite. It is the drama of a person who distrusts an idea, who tries to break it, who approaches it with skepticism, patience, and a kind of intellectual resistance, and who then discovers, to his own discomfort, that nature refuses to cooperate with his doubts. That is the story of Robert Millikan and Einstein's photoelectric equation. Because after Einstein proposed that light behaves, in some circumstances, as though it comes in discrete quanta, the idea did not sweep through physics in a wave of instant acceptance. Far from it. The proposal felt too disruptive, too costly, too offensive to the hard-won success of the wave theory of light. Many physicists could tolerate the photoelectric formula as a useful rule. Fewer were ready to accept Einstein's interpretation of what that rule meant. And Millikan was one of the skeptics. He was not the kind of experimentalist who approached a bold, theoretical idea with romantic enthusiasm. He did not want quantum language to run wild ahead of evidence. He wanted precision. He wanted disciplined measurement. He wanted a clean confrontation between equation and apparatus. And in that sense, he was exactly the kind of person Einstein needed. Because if a friendly admirer confirms your theory, people can always suspect sympathy. But if a skeptic tests it with ruthless care, and the numbers still line up, then something much more serious has happened. The theory has survived an adversarial trial. Millikan set out to measure the photoelectric effect with enormous accuracy, not casually, not with vague trends and suggestive hints. He wanted the relation between the stopping voltage and the frequency of the incoming light to be pinned down sharply across different metals, with every disturbance controlled as carefully as possible. Surface conditions mattered, cleanliness mattered, calibration mattered. This was not merely a conceptual dispute anymore. It was now a matter of exact slopes, exact thresholds, exact reproducible behavior. And the result, when it emerged, was deeply uncomfortable for anyone hoping Einstein's formula would simply go away. The data fell into a straight line. That point deserves to be lingered over. If Einstein's energy balance picture is correct, then the maximum kinetic energy of the emitted electrons should grow in a simple, steady way as the light's frequency increases. Since the stopping voltage measures that maximum kinetic energy, the stopping voltage itself should rise linearly with frequency, not loosely, not approximately in spirit, linearly. And that is what Millikan found. This is one of the most beautiful things in physics, when a conceptual idea suddenly becomes a geometric shape. Here, the shape was a line, a clean incline, a measured pattern that looked almost as though nature had signed Einstein's argument in ink. Why does this matter so much? Because a straight line means two different pieces of physical meaning are being separated with remarkable clarity. The steepness of that line tells you something universal. It reflects the ratio between the constant introduced by Planck and the charge of the electron. In plain language, it tells you how much additional stopping voltage is needed each time you raise the frequency by a given amount. That is not a property of one particular metal surface. It points toward a general law of nature. Meanwhile, the place where the line would intercept the voltage axis carries information about the metal itself. That offset reflects the work function, the energy cost required to liberate an electron from that material. So, the graph does something elegant. It cleanly separates what belongs to the universal rule from what belongs to the local material. That is why Millikan's experiment had such force. The slope whispered, "This is a universal constant." The intercept whispered, "This is the fingerprint of the metal." And together they said, Einstein's relation is not a lucky guess. It is structured, it is measurable, it is real. The photoelectric effect had already suggested that frequency mattered more deeply than classical wave theory wanted it to. But Millikan's measurements tightened that suggestion into something sharper. The stopping voltage did not wander unpredictably. It marched with frequency in a straight, disciplined line. That is the kind of pattern physicists trust. Now, there is another layer of beauty here, because Millikan's work also showed that one could extract Planck's constant from purely electrical measurements. Think about how astonishing that is. A constant first introduced in the strange bookkeeping of blackbody radiation now reappears in the behavior of electrons being knocked out of metals by light. Two apparently different physical situations are suddenly tied together by the same deep numerical thread. This is how theories gain weight. Not through rhetoric, not through elegance alone, but through recurrence. The same constant, the same pattern, the same structure, appearing in different corners of nature. By measuring the stopping voltage carefully, as the light frequency was varied, Millikan could infer the slope of the line. And from that slope, together with the known charge of the electron, he could back out the value of Planck's constant. In other words, the photoelectric effect became not just a conceptual puzzle, but a precision tool. It allowed a bridge to be built from optical behavior to one of the fundamental constants of the quantum world. That bridge is hard to ignore, because once an idea begins to generate the right numbers repeatedly in different materials, under different conditions, skepticism must change its character. It can no longer remain casual disbelief. It must either become a deeper, more sophisticated criticism, or it must start to yield. And here is where the irony sharpens. Millikan confirmed Einstein's equation, but he did not rush to embrace Einstein's full interpretation. He accepted the empirical success. He accepted the line. He accepted the extracted constant. But he remained uneasy about the notion that light itself, out in free space, should be thought of as genuinely particulate in character. That hesitation is historically important because it reminds us of something very subtle about science. A correct equation does not automatically settle the whole philosophical meaning behind it. That is one of the deepest lessons in this story. Sometimes, nature clearly endorses a relation before physicists fully agree on what picture of reality best explains it. A formula may work brilliantly, while interpretation remains unsettled. The numbers may be sharp, while the ontology stays blurry. That is not a weakness of science. It is one of its most honest features. Science often knows how to calculate before it knows how to narrate. And so, Millikan's result created a fascinating tension. On the one hand, the experiment made Einstein's photoelectric formula extremely hard to dismiss. The straight-line relationship was too clean, too reproducible, too revealing. The appearance of Planck's constant in this entirely different setting strengthened the sense that something genuinely new had entered physics. On the other hand, one could still hold back from saying that the light itself is made of quanta, in the same way a gas is made of molecules. One could still try to preserve some version of the classical wave picture for radiation itself, while allowing matter to respond in a quantized way. That middle position remained tempting. And this is what makes Millikan's role so memorable. He stands at the boundary between measurement and interpretation. He is the embodiment of a principle that runs through the best science. You do not have to love an idea in order to test it honestly. And if your own data corners you, then intellectual integrity requires that you say so. Science is not about loyalty to taste. It is about what survives contact with the apparatus. That sentence is worth letting settle, because it runs deeper than this one historical episode. Physics does not ask whether a theory feels comfortable. It does not ask whether it preserves older intuitions gracefully. It asks whether the world keeps returning the same answer when the experiment is repeated. And in Millikan's laboratory, the world kept returning Einstein's answer. Not all at once, and not with every philosophical tension resolved, but enough to shift the burden of proof. After Millikan, it was no longer easy to treat Einstein's photoelectric relation as a speculative curiosity. It had become experimentally disciplined. It had survived hostile scrutiny. It had acquired weight. Still, the old resistance had one refuge left. A critic could say, "Very well, the electron seems to receive energy in discrete amounts. Very well, Einstein's relation predicts the stopping voltage beautifully. Very well, Planck's constant appears again." But perhaps all of this tells us only about the internal structure of matter. Perhaps the metal surface and the electrons bound within it are the true source of discreteness. Perhaps the light wave remains fundamentally continuous, and the quantization appears only when matter responds to it. That was still a possible line of retreat, and that is why the story cannot stop here. Because Millikan had helped confirm that the exchange of energy in the photoelectric effect looks quantized. But had he proved that light itself carries not only energy, but something even more particle-like, something that behaves in collision the way an actual discrete object would? That is the pressure building toward the next chapter. Even so, could one still argue that the discreteness belonged only to the electron inside matter, while light remained fundamentally a wave? There is a special kind of experiment that changes the mood of physics, not because it introduces a new mystery, but because it takes an old argument and suddenly makes it brutally concrete. The photoelectric effect had already told physicists something deeply uncomfortable for the classical wave picture. Light did not seem to hand over energy in an endlessly smooth flow. It behaved as though energy arrived in separate packets, but there was still room for hesitation. A skeptic could still say that perhaps the discreteness belonged to matter, to electrons inside metals, to the strange way atoms respond to radiation. Then came Compton's scattering, and that refuge began to collapse, because now the question was no longer only about how light gives energy to matter. It was about whether light also carries momentum in the manner of a discrete projectile, and whether a collision with an electron could be read almost like an impact between two individual objects. Let us begin with the physical picture. Imagine a beam of X-rays aimed at a material whose electrons are only weakly bound, so weakly bound that for the purpose of the collision, they can be treated as almost free. The X-rays enter. Some of them scatter, but when physicists measure the scattered radiation, they find something subtle and astonishing. The outgoing X-rays do not all retain the same wavelength they had before. Instead, the wavelength changes, and not randomly. The amount of the change depends on the angle through which the radiation has scattered. That last detail is everything. If the scattered beam leaves at a small angle, the wavelength changes only a little. If it leaves at a larger angle, the wavelength change becomes larger. And if it is scattered almost backward, the change is larger still. In other words, the outgoing radiation is no longer identical to the incoming radiation. Something has happened during the encounter. Some of the light's original energy has been handed over to the electron, which recoils as a result. Now, if you are standing inside the classical wave picture, this is a very awkward thing to see, because in the ordinary wave treatment, an incoming electromagnetic wave shakes a charged particle, and that oscillating charge then re-radiates. Classical theory certainly allows scattering. It certainly allows radiation to be redirected, but it does not naturally predict this clean, angle-dependent shift in wavelength of the scattered X-ray. It does not naturally describe the event as though a single piece of light arrived, struck a single electron, lost part of its energy and momentum, and departed altered. But that is exactly the picture that suddenly begins to make sense here. And once that particle picture is brought in, the experiment becomes almost unnervingly readable. Think of it this way. Before the collision, the light quantum is moving toward the electron, carrying both energy and momentum. The electron, initially nearly at rest, is simply waiting. Then the encounter happens. Afterward, the outgoing light quantum has changed direction. The electron has been kicked away. So whatever description we use must respect two great bookkeeping laws of physics. Total energy must be conserved, and total momentum must also be conserved. The incoming light quantum carries energy tied to its frequency, or equally tied to its wavelength. Shorter wavelength means higher energy. It also carries momentum, and the shorter the wavelength, the larger that momentum. That relationship had already been quietly implied by earlier quantum ideas, but here it becomes physically tangible. The light is no longer merely energetic. It arrives with something directional, something push-like, something collision-ready. Then the collision takes place. The outgoing photon flies off at some angle. The electron recoils in another direction. And because both energy and momentum must balance before and after the encounter, the outgoing photon cannot generally keep the same energy it had at the start. Some has gone into the motion of the electron. That means the scattered photon must emerge with lower energy than before, and since lower energy corresponds to lower frequency, and therefore longer wavelength, the wavelength increases. That is the essence of the Compton shift. Now let us slow down and walk through the logic more gently, because this is one of those places where the physics becomes beautiful precisely. Start with the incoming photon. It approaches with a certain wavelength, and therefore with a definite energy and momentum. You do not need to memorize the symbols to grasp the structure. Short wavelength means a more energetic, harder-hitting quantum. The X-ray range is especially useful because these quanta are energetic enough that their collisions with electrons are measurable in a clear way. Next, consider the electron. At the start, we treat it as essentially at rest. That simplification matters because it means the initial momentum of the whole system belongs almost entirely to the incoming photon. The electron is not already racing through the lab with some large unknown motion. It is waiting, almost still, ready to be struck. Then comes the interaction. Afterward, the outgoing photon is no longer traveling in its original direction. It has scattered away by some angle. If it changes direction, then the momentum bookkeeping becomes two-dimensional. There is not just a before and after along one line. We now have to account for how much momentum remains in the original direction and how much has turned sideways. The recoiling electron must pick up whatever momentum is needed to make the total balance work. And this is where the angle dependence enters naturally. A small deflection means the photon keeps much of its original forward momentum. The electron recoils, but not dramatically, so the photon does not need to surrender very much energy. The wavelength shift is small. A larger deflection means the photon has changed direction more severely. That requires a larger rearrangement of momentum. The electron must take up more of the difference. And to make that happen while conserving energy as well, the photon must leave with less energy than before. Its wavelength grows more noticeably. At the largest scattering angles, the change becomes greatest. This is not random. It is not a messy detail of the target material. It is a geometric consequence of collision plus conservation. The photoelectric effect told us that light transfers energy in discrete packets. Compton scattering goes further. It tells us that those packets also carry momentum in a way that matters during a collision. The outgoing wavelength changes because the photon gives some of its energy and momentum to the recoiling electron. At this point, the particle-like language is no longer decorative. It is doing real explanatory work. And now we can see why the famous Compton formula has such force, even if we do not dwell on its algebra line by line. The wavelength shift is predicted to depend only on the scattering angle and on a combination of constants involving Planck's constant, the electron's mass, and the speed of light. In words, that means the size of the shift is not determined by the color of the target material, not by chemical quirks, not by some obscure internal resonance. It is set by the geometry of the collision and the universal properties of the participants. That is exactly the kind of result physicists trust. Because when a phenomenon turns out to depend on universal constants and simple geometry, it begins to look less like a special trick and more like a window into structure. The electron mass enters because the electron is the object being kicked. A heavier object would recoil differently. A lighter one would recoil more easily. The scattering angle enters because changing direction is part of the momentum transaction, and the shift toward longer wavelength tells us, in plain language, that the outgoing photon has been diminished. It is still there. It still survives the collision, but it has lost some of its original energy to the electron. That last point is especially powerful. In the photoelectric effect, the incoming quantum seemed to vanish into the electron, handing over its energy in a single event. But in Compton scattering, the light quantum survives and exits the collision altered. That makes the particle picture even harder to avoid. We are no longer only talking about an emission event from matter. We are talking about a two-body encounter in which the light behaves like a participant with both energy and momentum, not merely like a spread-out wave that somehow shakes the electron from afar. This is why the Compton effect felt so decisive. A wave account can certainly describe scattering in broad terms, but the specific angle-dependent wavelength shift fits beautifully into the collision picture and awkwardly into the classical one. The photon comes in, strikes the electron, recoils with reduced energy, and leaves. The electron is kicked away. The bookkeeping works. The measured shift matches the prediction. That is a very strong kind of evidence. The experimental importance of this cannot be overstated. By the time physicists took Compton scattering seriously, the light quantum idea had moved beyond being just a clever explanation for a puzzling metal surface. It had become a framework capable of describing a direct collision. The American Physical Society later recognized the Compton effect as a historic turning point because it showed that light could not be explained purely as a wave. It behaved as though it were a stream of particles with energy proportional to frequency. That phrasing matters, not merely energetic wavefronts, particles, streams, collisions. And once the word momentum becomes unavoidable, the old resistance becomes harder to maintain. Remember the refuge that skeptics still had after the photoelectric effect. They could still say that perhaps discreteness belongs only to the electrons in matter. Perhaps the metal is quantized. Perhaps the detector is quantized. Perhaps matter responds in jumps while light itself remains a continuous wave. Compton scattering weakens that refuge dramatically. Because now the light must arrive carrying a directional, transferable impulse of its own. The shift in wavelength depends on the collision geometry in exactly the way one expects if the light quantum itself has momentum. This is not merely matter chopping up a continuous field at the moment of detection. This is the light entering the encounter already equipped for impact. That does not yet tell us everything. It does not yet solve the mystery of interference. It does not yet tell us how a photon spreads or what a quantum field really is. or how something can behave in wave-like and particle-like ways without collapsing into contradiction. Those deeper questions are still ahead, but it changes the balance of the argument. The photoelectric effect showed that light transfers energy in discrete packets. Compton scattering showed that those packets also carry momentum. Together, these results pushed the particle-like description from an optional interpretation to a serious physical necessity. Light was no longer merely acting as if it were quantized in some bookkeeping sense. It was beginning to act like a genuine collision partner. And that leaves us with the next danger. Because if photons carry both energy and momentum like particles, if they strike electrons and recoil from collisions, does that mean light is secretly made of tiny classical balls after all? At this point in the story, there is a very tempting mistake waiting for us. It is the kind of mistake that feels satisfying for a moment because it gives the mind something familiar to hold. We have seen light transfer energy in discrete amounts. We have seen it deliver momentum in collisions. We have watched it behave in several crucial experiments, as though it arrives in individual packets, and so the imagination reaches for the nearest available picture. Fine, we say. Then light must really be made of tiny little balls, tiny bullets, tiny pebbles, tiny Newtonian corpuscles, brought back from the dead under a new name. But that conclusion, however natural it feels, is exactly the wrong place to stop. Because the photon is not a miniature marble drifting through space on a neat little path. If it were, the rest of optics would fall apart. Let us begin with the classical particle. A classical particle is, above all, a thing with a definite story. It is here, not there. It has a position. It moves along a path. If you know where it is and how fast it is moving, then in principle you can say where it will go next. A thrown stone follows an arc. A bullet follows a trajectory. A grain of dust drifts along a track through the air. This is the kind of mental picture that classical mechanics trains us to trust. Even when we do not know every detail, we still imagine that the details exist. The object has a location, a direction, a speed. Reality, in this picture, is made of definite facts waiting to be discovered. That is what makes the particle language feel so comforting. And after the photoelectric effect and Compton scattering, it becomes incredibly tempting to place the photon inside exactly that frame. It carries energy, so we imagine a tiny carrier. It carries momentum, so we imagine a tiny impactor. It arrives as a local event in a detector, so we imagine a tiny object that must have traveled from source to detector more or less the way a pebble travels from hand to window. But the photon refuses to behave that way, because the moment we try to treat it as a classical little ball, we run straight back into the very experiments that once made wave theory so powerful: interference and diffraction. A little ball does not naturally produce an interference pattern with itself. A little ball does not spread through two slits and generate alternating bands of brightness and darkness. A little ball does not bend around openings the way light does. And yet the photon unmistakably does. The defenders of waves were right about something profound. Light really does produce interference and diffraction. Those are not illusions. They are not historical misunderstandings. They are among the most secure facts in all of physics. But the defenders of pure continuity were also incomplete, because the transfer of energy and momentum in detection events is discrete. So the photon carries us into a domain where the old classical categories no longer fit cleanly. And nowhere is that more striking than in the single photon double-slit experiment. Imagine sending light toward a barrier with two narrow slits, just as in Young's classic interference experiment. But now turn the intensity down so far that the apparatus is effectively sending one photon at a time. Not a bright beam, not a rush, a lonely sequence of individual events, one detection, then another, then another. What would a classical little ball picture suggest? It would suggest that each photon chooses one slit or the other and lands somewhere on the screen accordingly. Over time, you might expect a pileup corresponding to two smeared-out bands, perhaps softened by imperfections, but still broadly particle-like. After all, if each photon is just a tiny object taking one route, then the final distribution should look like the sum of two ordinary streams. But that is not what happens. What happens is much stranger. Each individual detection is local, a single click, a single dot. The screen does not register a smeared wave of half energy everywhere. It registers an event in one place. Then another event in one place. Then another. Every arrival looks particle-like in that sense, localized, discrete, countable. And yet, when enough of these single events are accumulated, the overall pattern that gradually appears is not the simple sum of two classical streams. It is an interference pattern. Bright regions where detections are common, dark regions where detections are rare. The same kind of striped architecture that waves produce. That single fact is enough to destroy the idea that a photon is just a tiny classical ball. Because a classical ball arrives locally, yes, but it does not build up an interference pattern, one discrete arrival at a time, unless something deeper, something wave-like, is shaping the probabilities of where those arrivals occur. The photon does behave in a particle-like way when it is detected. The detector clicks here, not everywhere. Energy is exchanged in discrete units. Momentum is exchanged in discrete units. But the distribution of many such events is governed by an interference structure that no classical stream of little pellets can explain. So, particle-like does not mean classical particle. That is the crucial distinction. A photon is not wave-like in the way a water ripple is wave-like, because a water ripple spreads continuously through a medium and can, in principle, be measured as a distributed disturbance. And a photon is not particle-like in the way a tiny stone is particle-like, because a stone follows a definite path through one slit or the other without generating a self-interference pattern. The photon lives somewhere deeper than both analogies. In classical optics, the intensity of light tells you how much energy the wave is carrying across space. Brighter regions correspond to a stronger electromagnetic disturbance. That picture works beautifully for many purposes, and it survives in an important, transformed way inside quantum theory. But now, the meaning shifts. In the quantum picture, the classical intensity pattern becomes related to the likelihood of where a photon will be detected, not where a little ball really was in the hidden classical sense, not where a tiny object secretly traveled along a sharp path while we were not looking, but where a detection event is more or less probable. This is one of the hardest transitions in all of physics, not because the equations are impossible, but because the mind resists giving up its old habits. We want an object to have a fully classical biography. We want to say, it started here, moved there, passed through this slit, missed that one, and then landed at that exact point for ordinary mechanical reasons. Quantum theory tells us that this demand is too crude. Instead, what evolves through the experiment is something more abstract and more powerful, a probability amplitude, a structured mathematical object that behaves in a wave-like manner, spreading, combining, and interfering. Where this amplitude reinforces itself, detections become more likely. Where it cancels, detections become less likely. The final individual event is still local, still discrete, still particle-like at the detector. But the pattern governing those events is wave-like in its architecture. That is why the old words begin to fail us. We should be careful here not to rush into unnecessarily formal language. We do not yet need the full machinery of quantum field theory. We do not need to bury the story under technical symbols. What matters at this stage is the conceptual bridge. The bridge is this. Classical waves tell you about intensity spread through space. Quantum theory turns that spread into a map of detection likelihood. So when you send many photons one by one through a double-slit apparatus, you do not see each photon arriving as a classical wave smeared across the screen. You see discrete clicks, but the relative frequency of those clicks across many trials traces out the same interference architecture that wave theory would have predicted for intensity. That is not a compromise between wave and particle. It is something stranger. The photon is a quantum object whose propagation and whose detection belong to different layers of description. In motion, it is governed by a wave-like amplitude. In detection, it appears as a localized event. This is why people often say, a little too casually, that light is both a wave and a particle. The sentence survives because it gestures toward a truth. But it misleads if taken too literally, because it makes it sound as though light is simply half one thing and half another, or somehow a hybrid made by gluing two classical pictures together. That is not right. The actual lesson is harsher and more beautiful. The world, at the quantum level, is not built to satisfy the categories that evolved from human encounters with stones, water, arrows, and dust. And the photon is one of the first places where that becomes impossible to ignore. It does not spread like a pond ripple in any ordinary material medium. It does not travel like a pebble with a perfectly classical hidden route. It is not a tiny billiard ball. It is not a little splash of water. It is a quantum entity that forces us to separate two ideas we once assumed belonged together: the continuous evolution of a possibility pattern and the discrete localization of an actual detection. That sentence may sound abstract, but it is really just a more honest way of saying what the experiments already told us. Photoelectric effect, discrete transfer, Compton scattering, discrete momentum in collision, single photon interference, wave, like structure in the pattern of outcomes. Put them together, and the old language bends under the weight. This is also why it is so important not to oversimplify the meaning of detection. When a detector registers a photon in one place, that does not automatically prove the photon had a classical little ball position all along. It proves that the interaction with the detector is localized. That is a subtler statement. It tells us how energy and momentum are delivered in measurement. It does not grant us permission to sneak the whole classical worldview back in through the side door. And the same is true for interference. The fact that many detections form a wave-like pattern does not mean each photon was literally a classical water wave spread out in the old sense. It means the mathematical structure that governs outcomes evolves in a way that has interference built into it. So the photon stands in an extraordinary middle ground, not between wave and particle as a compromise, beyond them as a challenge. Particle-like does not mean classical particle. For the photon, it means that energy exchange is discrete, momentum exchange is discrete, and detection events are localized. At the same time, the distribution of many such events is governed by a wave-like probability structure that produces interference and diffraction. The photon is therefore neither a little ball nor a little water ripple. It is a quantum object, and our everyday language strains to keep up. And that leaves us exactly where quantum theory wanted to take us. If light is neither a classical wave nor a classical particle, what exactly does quantum theory say it is? By now, the old language has taken us as far as it can. We have seen light behave in ways that forced physicists to talk about packets of energy. We have watched those packets carry momentum. We have seen that detection happens in localized clicks, while interference still survives with full strength. So the temptation is to keep saying over and over that light is a particle, and to hope that repeating the phrase will somehow make the strangeness feel resolved. But modern physics does not actually end there. In fact, that sentence, useful as it once was, is no longer the deepest version of the truth, because the most modern view is not that light is fundamentally a little thing traveling through space. It is that the electromagnetic field is fundamental, and what we call a photon is the smallest allowed excitation of that field. In classical physics, the electromagnetic field is continuous. That word matters. It means the field can be stronger or weaker by any amount. It can ripple through space in endlessly smooth ways. It can be decomposed into different frequencies, different patterns, different modes of vibration. There is no built-in smallest unit of fieldness. Just as a violin string can vibrate in many different harmonics, the electromagnetic field can sustain many different oscillatory patterns. Maxwell's theory describes this world with extraordinary beauty. Light is not a substance sitting inside the field. Light is the field in motion. And that picture was not thrown away by quantum theory. That is one of the most important points in this entire story. Quantum physics did not arrive and say, Maxwell was useless, or that waves were an illusion, or that the field should be replaced by tiny flying pellets. Quite the opposite. The field survives. The wave structure survives. The propagation survives. What changes is not the existence of the field, but the rules for how its energy is allowed to appear and be exchanged. That is the conceptual shift. To see it more clearly, physicists learn to break the field into modes. A mode is one independent pattern in which the field can oscillate, much like a single pure musical note in a much richer sound. In a cavity, or in free space treated mathematically, the full electromagnetic field can be described as a collection of these independent patterns. Each one has its own frequency. Each one can carry energy. Now comes the key move. Instead of thinking of each field mode as a purely classical oscillation that can store any arbitrary amount of energy, quantum theory asks us to treat each mode the way it treats a quantum harmonic oscillator. That phrase may sound technical, but the intuition behind it is gentle. A harmonic oscillator is simply a system that likes to move back and forth around an equilibrium point, a mass on a spring, a pendulum swinging in small arcs, a musical vibration returning rhythmically again and again. In classical physics, such an oscillator can carry any amount of energy: tiny motion, medium motion, large motion, anything in between. But in quantum mechanics, that freedom is restricted. The oscillator can no longer possess just any energy it pleases. Its energy comes in steps, not a smooth slope, a staircase. And here is the remarkable insight. Each mode of the electromagnetic field behaves in precisely this staircase-like way. This is where the photon enters in its mature form. One step of excitation in a field mode corresponds to one photon. Two steps correspond to two photons in that same mode. Three steps, three photons, and so on. In other words, the photon is not a little object added to the field from the outside. It is the field excited by one quantum. The field remains primary. The photon is what one unit of field excitation looks like when energy is transferred or detected. That is a much deeper statement than simply saying light is a particle, because now the particle-like aspect is no longer the foundation. The field is the foundation. What appears particle-like is the quantized way in which that field can be excited and the localized way in which those excitations are exchanged in measurement. This is one of the great conceptual achievements of 20th century physics. It reconciles, in a much more mature way, the two halves of the story we have been carrying. The wave behavior of light was real all along because the field is real all along. The discrete packets of energy were also real because the field does not hand over energy continuously. It does so in quanta. Once that is understood, the older tension begins to soften. The classical electromagnetic field does not disappear in quantum theory. It remains, but its allowed excitations are no longer continuous. Each mode behaves like a quantum oscillator, which means it can only be excited in discrete steps. A photon is one such step, the smallest transferable excitation of the electromagnetic field. Imagine a perfectly still violin string, not moving at all. Then imagine exciting it in its simplest note, then more strongly, then in higher harmonics. Classical thinking invites you to imagine that the string's energy can be adjusted smoothly, like turning a dial. Quantum thinking says, for each allowed vibrational pattern, the energy does not behave like a free dial. It behaves like counted rungs. You may stand on the first rung, or the second, or the third, but not halfway in the old classical sense. Now translate that from string to field. The electromagnetic field fills space. It has allowed modes of vibration. Each mode behaves like a quantum oscillator, so the energy associated with that mode comes not as a continuous pour, but in discrete units. One unit is one photon. This does not mean that the field itself is made of little beads. It means the excitations of the field are quantized. That distinction is everything. Because once you say the field is fundamental, many earlier puzzles begin to rearrange themselves in a healthier way. Interference no longer feels embarrassing because fields naturally interfere. Diffraction no longer feels like a leftover from the wave theory that we are awkwardly trying to preserve. It is built in from the beginning because the underlying entity is still a field extended across space. At the same time, the photoelectric effect and Compton scattering no longer feel like strange exceptions because quantized excitations naturally deliver energy and momentum in discrete exchanges. So the photon becomes easier to understand if we stop imagining a tiny ball and start imagining a field that is only allowed to hand over its vibrational energy in fixed units. There is another subtle point here, one that often passes unnoticed in popular explanations. When physicists say, one photon in a mode, they are not describing a little object that must already possess all the properties of a classical particle at every moment. They are describing the state of the field. That is a very different kind of language. It is less pictorial, perhaps, but more faithful. The field can be in a state corresponding to one quantum of excitation, or two, or many. And the probabilities for what a detector will register arise from that quantum state. So the modern story is not merely light is a wave sometimes and a particle sometimes. The modern story is the electromagnetic field is quantized, and what we call photons are its discrete excitations. Wave-like behavior comes from the field structure. Particle-like detection comes from the quantized exchange of those excitations. This is why the modern framework feels so much more satisfying than the older slogan. It does not force us to imagine light-changing costumes depending on who is watching. It tells us instead that our classical categories were always too small. The field picture contains the wave logic naturally, and quantization contains the particle logic naturally. Neither side needs to be patched in as an afterthought. And yet, even here, one should feel a small tremor of unease. Because if the field is the true underlying entity, and photons are just quantized excitations of that field, then why does the world of measurement still look so lumpy? Why does a detector not simply register a gentle field spread continuously over its surface? Why does it click at one place, one moment, as though a discrete little event has occurred? That question is not a flaw in the theory. It is the next doorway. The deepest modern statement is not, light is fundamentally a particle. The deepest statement is that the electromagnetic field is fundamental, and the allowed excitations of that field are quantized. A photon is one quantum of excitation in a field mode, the smallest unit the field can transfer. The wave picture survives because the field survives. The discreteness survives because the excitations are quantized. That is the mature answer, but it immediately gives birth to the next mystery. If the field picture is so powerful, why do detectors still register light one click at a time? There is a moment in almost every deep scientific story when the abstractions must return to the bench, to the instrument, to the place where nature stops being a beautiful idea and becomes a readout. Up to now, we have built a long arc. We began with waves that seemed to explain everything. We watched continuity fracture under the pressure of blackbody radiation. We followed Einstein's dangerous leap, the photoelectric effect, Compton scattering, and the rise of the photon. Then we took the more modern step and said something even deeper. The electromagnetic field is fundamental, and photons are quantized excitations of that field. But there is still a very human question waiting in the room. If that is really the right picture, then what do actual detectors see? What does a machine, built with wires and glass and semiconductors and cryogenic metals, encounter when light arrives? And the answer is one of the reasons the photon idea became impossible to treat as merely philosophical, because detectors do not register a smooth mist of partial light. They register events, localized, countable, reproducible events. Let us begin with the instruments. The details differ, but the central drama is the same. A detector does not merely look at light in some passive, ghostly sense. It interacts, it absorbs. It converts the arrival of light into some electrical or measurable consequence. In a photomultiplier tube, light strikes a surface and liberates an electron through the photoelectric effect. That single liberated electron is then accelerated and multiplied again and again through a cascade until one tiny event becomes a measurable electrical pulse. In an avalanche photodiode, the absorbed light triggers a charge carrier that is then amplified inside the semiconductor into a sharp signal. In a CCD or CMOS sensor, light creates charge in individual pixels, and those charges are later read out as the image. In superconducting detectors, the arrival of even one quantum can disturb a fragile, low-temperature state enough to be noticed with exquisite sensitivity. Different technologies, different engineering, same underlying lesson. Detection is not experienced by the apparatus as a smooth classical wave washing evenly across all possibilities. Detection happens as an event in matter, and that word event is more important than it may sound at first, because in ordinary life, we are used to fields acting gradually. Heat diffuses, pressure spreads, water dampens a surface. But when a single photon detector is operating in the right regime, the arrival of light is not recorded as a faint haze that is infinitely divisible in practice. It is recorded as a localized occurrence, a click, a pulse, a pixel event, a transition in a superconducting element. Something happened here, at this moment. This does not mean the detector has revealed a tiny classical bead hiding underneath the theory, but it does mean that the interaction between light and matter is operationally discrete. That is a very strong statement. To feel why this matters, imagine what a purely classical wave picture might tempt us to expect. If an incoming electromagnetic wave is spread broadly and continuously, perhaps one imagines the detector receiving little fractional dribbles of energy everywhere, as though the wave simply stains the apparatus in proportion to its local amplitude. And indeed, in high-intensity settings, classical descriptions remain extraordinarily useful. But when the light is made weak enough, when one enters the regime of single quanta, the world of detection becomes lumpy, not smoothly lumpy, sharply lumpy. The detector either fires or it does not. A given pixel either records a charge event or it does not. A given timing circuit either registers a pulse or it does not. That is what a click means. A click is the experimental face of quantization. It is the operational signature that energy was not shared out in an arbitrarily fine mist during that interaction, but was delivered in a discrete transaction. The entire quantum relevant to that detection is absorbed in the event. The detector does not take 1/3 of a photon now, 1/5 later, and the rest after t. The interaction is whole. In the detection process, the field transfers one allowed unit of excitation into matter. This is why the old photon language survives so stubbornly. Not because physicists enjoy little metaphors, but because the detectors keep behaving as though the exchange comes in countable quanta. And once again, the photoelectric effect quietly returns at the foundation of much of this technology. Some of the most important photodetectors ever built rely directly or indirectly on the same principle Einstein used to explain electron emission. Light arrives, energy is transferred in a discrete way, and matter responds by releasing or rearranging charge. That is one reason the later ability to count and manipulate quanta of light became so central to modern physics. The Nobel Prize in Physics in 2005, awarded for work involving optical coherence and the behavior of light quanta, reflected how profoundly modern measurement had entered this regime of counting, detecting, and controlling individual quantum events. Theoretical language becomes trustworthy in physics when it connects to apparatus, and apparatus tells us this. In the appropriate regime, light is not merely something that spreads. It is something that triggers localized, countable detection events. A click matters because it is the experimental trace of a discrete exchange between field and matter. Now, we should be careful here, because it is easy to overstate what a click proves. A click does not prove that a photon was a tiny marble with a fully classical trajectory all along. A click does not mean we can simply forget the field picture and go back to 19th century corpuscles. A click tells us something subtler and more durable. When the electromagnetic field interacts with matter in a detection event, the transfer occurs in quantized units, and the detector registers that transfer locally. That is already enough to be powerful. And modern experiments go even further. One of the most beautiful modern signatures of truly single-photon light is something called anti-bunching. The name sounds technical, but the idea is intuitive once you sit with it. Classical light sources, or fields treated in purely classical statistical ways, tend to produce detection events that can cluster in certain familiar patterns. But a genuine single-photon source behaves differently. When one photon is present, it is not available to trigger two independent detections at the same time in the way a classical wave might naively seem able to spread its influence. If you send such light toward a setup that asks, in effect, do we see simultaneous arrivals at two places? The answer for a true single-photon regime is suppressed in a very distinctive way. Not absolutely impossible under every real-world condition, because experiments are never infinitely perfect, but suppressed enough to reveal that we are not dealing with an ordinary classical field picture. One photon does not split itself into two full, simultaneous detection events. One quantum produces one event. That is the deep meaning behind anti-bunching. It is not just another laboratory curiosity. It is a modern statistical fingerprint of the discreteness of light. It tells us, through timing correlations, that the source is producing light in a way that cannot be comfortably reproduced by classical wave language alone. And notice how this builds on everything that came before. The photoelectric effect taught us that light transfers energy in packets. Compton scattering taught us that those packets carry momentum. Single photon interference taught us that the distribution of events is still governed by wave-like probability structure. And now detector statistics teach us that the event structure itself has a grain, a one-by-one character, a measurable discreteness that remains visible even in the timing of arrivals. This is why the detector chapter matters so much. It is where philosophy gets disciplined. One can argue endlessly in words about what is really real. One can prefer waves, fields, particles, quanta, excitations, or operationalism. But in the laboratory, nature has the habit of answering through behavior. And one of the cleanest lessons behavior gives us is this: the theory that includes photons predicts what detectors do far better than a theory that insists on purely continuous classical light in all circumstances. That sentence contains a deep truth about physics as a whole. Reality, in practice, often means stable, reproducible, operational behavior. Not because physicists have no taste for deeper metaphysics, but because apparatus is how theory meets the world. If a concept repeatedly organizes what instruments do, predicts how signals scale, explains why clicks occur one at a time, and accounts for the observed statistics of detection, then that concept earns its place. The photon earned its place that way. Not by charm, not by linguistic convenience, by repeated experimental obedience. There is something almost poetic, though not in a decorative sense, about how humble the final evidence can look. After all the grand theories, after Maxwell, Planck, Einstein, Compton, after all the conceptual upheaval, the modern laboratory often reduces the question to something nearly childlike in its simplicity. Did the detector click, and when? And yet inside that simplicity lies the weight of a century, because the click is not alone. It belongs to a structure, to calibrated detectors, to frequency dependence, to discrete thresholds, to scattering shifts, to interference built one event at a time, to anti-bunching, to quantum optics, to superconducting sensitivity, to reproducible statistics. A single click is humble. A world of clicks, behaving exactly as photon theory predicts, is profound. Detectors matter because they turn the abstract into the measurable. They do not passively see a smooth wave in the old everyday sense. They register localized events. In the single quantum regime, one detection corresponds to the absorption of one allowed excitation of the electromagnetic field. Modern evidence, such as anti-bunching, strengthens this picture further by showing that single photon light has timing statistics that resist classical explanation. This is why physicists believe in photons, not because the word is attractive, but because the theory built around photons keeps predicting what detectors actually do. And yet, even here, a strange discomfort remains. If photons are so well established, if the experiments are so strong, if the detectors keep clicking in exactly the right ways, why do so many people still feel uneasy with the statement that light is a particle? By now, we have earned the right to ask the most dangerous question in the entire story, not the historical question, not the experimental question, not even the mathematical one, the philosophical one. After all the evidence, after the blackbody crisis, after Einstein's leap, after the photoelectric effect, after Compton scattering, after single photon interference, after the quantized field and the clicks of real detectors, why does the sentence still feel so awkward? Why do so many people hear light is a particle and immediately feel that something has been lost, something has been oversimplified, something has been forced into words that do not quite fit? The answer is that the unease is justified, because the final mistake would be to think that this story ends by choosing one familiar label over another. It does not. The deepest lesson is that wave or particle was never the right final question. First, we need to confront a hard truth. The categories of everyday life were built from everyday scales, and they begin to fail in the quantum world. Then, we will look at the idea of complementarity, the insight associated above all with Niels Bohr, which tells us that different experimental arrangements can bring out different aspects of the same underlying reality. Next, we will gather the lessons of the whole series into one coherent statement. When light propagates freely, wave-like structure dominates the description. When light exchanges energy and momentum in measurement, localized discrete events dominate the description. After that, we will state carefully what physicists actually mean when they say they believe in photons. And finally, we will prepare the closing answer to the original question. Let us begin with the most uncomfortable part. Human language was not built for quantum mechanics. Our deepest everyday categories were shaped by ordinary objects at ordinary scales. We know what a stone is because we can hold it. We know what a wave is because we can watch water, sound, rope, and wind. We learn these categories through contact with a world of medium-sized things, so we naturally expect reality to respect them. We expect the world, at its foundations, to be built from items that are either one kind of thing or the other. But quantum physics keeps refusing that demand. Light is one of the first places where the refusal becomes undeniable. If we insist on asking whether light is really a wave, or really a particle in the old classical sense, we keep running into experiments that punish our stubbornness. When we try to make light purely wave-like, discrete transfer and localized detection events push back. When we try to make light purely particle-like, interference and diffraction push back. The trouble is not that one side is right and the other side is wrong. The trouble is that both words carry too much classical baggage. That is the trap. The words wave and particle remain useful, but only if we remember that they are analogies pointing toward features of behavior, not complete definitions of what the object is in itself. This is where Bohr's idea of complementarity becomes so important. Bohr's great philosophical contribution was not to make quantum theory mystical or vague, as it is sometimes unfairly portrayed. It was to insist, with unusual seriousness, that the form in which a quantum phenomenon appears depends on the experimental context. The arrangement of the apparatus, the type of question asked, the structure of the measurement, these are not decorative details. They shape what aspect of the quantum object becomes manifest. In one kind of setup, wave-like propagation is the right language. In another, particle-like localization is the right language. The two descriptions are not simply enemies. They are complementary. Each reveals something real, but neither alone is complete. We have already seen this in practice. When light propagates freely through space, especially through an arrangement like a double slit, the description that works is wave-like, not in the sense of tiny water ripples sloshing through a material medium, but in the sense that what evolves is extended, spread out, capable of interference, sensitive to phase, capable of producing diffraction and patterned probability distributions. If we try to erase that wave-like structure, we lose the ability to explain some of the most basic and beautiful phenomena in optics. But when light exchanges energy or momentum with matter, especially in a detection event, something else becomes prominent. The event is localized. The transfer is discrete. The apparatus does not register a smooth drizzle of partial energy everywhere. It records a click here, a pulse there, an electron knocked free, a single detector element firing, a charge packet appearing in one pixel. In this context, the particle-like character becomes unavoidable. And so the measurement context matters, not because the world is inconsistent, not because light is indecisive, but because our classical categories each capture only one face of a deeper quantum structure. That is why the sentence, "light is both a wave and a particle," is simultaneously useful and misleading. It is useful because it warns us not to cling too tightly to one classical picture. But it is misleading because it sounds as though light is made by fusing two old objects together, as though nature took half a pond ripple and half a pebble and stitched them into one hybrid. That is not what quantum theory is telling us. Quantum theory is telling us something more radical. The underlying object is not classical at all, and the classical words survive only as partial shadows cast by different kinds of experiments. Everyday categories fail in the quantum domain because they were built for a different scale of reality. Bohr's complementarity tells us that different measurement contexts reveal different aspects of the same underlying quantum entity. Light propagates in a wave-like way through space, but when it is detected, it appears through localized, discrete events. The contradiction softens once we stop demanding that one classical label must win completely. Now we can finally say, with more precision, what physicists do and do not mean when they say they believe light is a particle. They do not mean that light is a classical little object with a permanently definite position, trajectory, and velocity in the old Newtonian sense. They do not mean that the wave description was a historical error that should be thrown away. They do not mean that the field picture is merely a convenient decoration sitting on top of hidden billiard balls. What they do mean is much more careful. They mean that light possesses discrete quanta. They mean that these quanta carry definite amounts of energy and momentum related to the frequency and wavelength involved. They mean that those quanta are detected as localized events. And they mean that the most complete modern description of all of this is not tiny particles flying through empty space, but the quantum description of the electromagnetic field and its allowed excitations. That is the mature answer. This is also why the phrase, "believe light is a particle," needs to be handled with care. In one sense, yes, physicists do speak this way, because the particle-like language points towards something experimentally indispensable: discrete quanta, localized detections, energy and momentum transfer in individual events. In that operational sense, the statement is absolutely justified. But in a deeper sense, physicists do not stop there. They know that if the phrase is heard too classically, it immediately breeds confusion. People imagine tiny beads, miniature bullets, definite microscopic tracks hiding behind every event. Then the double-slit experiment returns and humiliates that picture all over again. So the wise thing to say is not merely that light is a particle. The wise thing is to say that the particle-like aspect of light is real, but it emerges within a deeper quantum framework that is not exhausted by classical particle language. This is one of the quiet beauties of physics. The goal is not to preserve common sense at all costs. The goal is to let reality teach common sense how to grow. And once you see the story that way, the whole journey begins to feel less like a contradiction and more like an education. We began with categories that felt obvious: wave, particle, continuous, localized. Then experiment kept telling us that none of these labels could bear the full weight alone. At first that feels frustrating. Then, slowly, it becomes liberating. Nature is not obligated to respect the first vocabulary that humans found convenient. That is not a defect in the universe. It is one of the reasons the universe is worth studying. Because the truth, again and again, turns out to be deeper than the labels we first attach to it. And light is perhaps the perfect teacher of that lesson. It begins as something we think we understand: illumination, color, radiance, the ordinary medium of sight itself. Then physics follows it more carefully and discovers that inside that familiar glow lives one of the most profound revolutions in thought ever forced upon the human mind. That is why this chapter matters so much. It is not merely there to tidy up a paradox from popular science. It is there to warn us against a false simplicity. A childlike story can say, wave or particle, and demand a winner. Physics, after a century of struggle, answers more honestly. The demand itself is too crude. So the final philosophical picture is this. Light is not a classical wave. Light is not a classical particle. Light is a quantum field phenomenon whose excitations are discrete, whose exchanges of energy and momentum are quantized, whose detections are localized, and whose propagation is governed by wave-like probability structure. That sentence is heavier than the old slogan, but it is far closer to the truth. And perhaps that is the deepest achievement of the whole story. We did not end by choosing between two comforting images. We ended by outgrowing both. We do not believe light is a particle in the sense of an ordinary tiny object. We believe that light comes in discrete quanta, that these quanta carry definite energy and momentum, that they are registered in localized detection events, and that the complete modern description is quantum and field-based. The phrase wave or particle survives only as a rough doorway. Beyond that doorway, the real structure is richer. And now, after all this history, all these experiments, all these conceptual repairs, only one task remains. So after all this history, math, and experiment, we can finally return to the original question and ask what the cleanest possible answer really is. Why do we actually believe light is a particle? Not in the loose, popular sense. Not in the lazy textbook sense. Not in the sense of repeating a famous phrase because quantum mechanics is supposed to sound strange, but in the serious sense, in the historical sense, in the experimental sense, in the sense of asking what nature forced physicists to accept, even when acceptance came slowly, reluctantly, and at the cost of older intuition. At first, waves seem to have won, and they deserve to win. That is the first thing we had to learn. The wave theory of light was not some foolish mistake waiting to be corrected by clever modern physics. It was one of the great triumphs of science. It explained interference, where overlapping light creates bright and dark bands. It explained diffraction, where light bends and spreads through narrow openings. It explained polarization. And then Maxwell arrived and did something even greater. He showed that light belongs to the electromagnetic field itself. Suddenly, light was no longer just wave, like by analogy. It was part of a unified, mathematical description of nature. Electricity, magnetism, and light were woven together in one astonishing framework. At that stage, the case seemed almost finished. Then came the crack. Blackbody radiation revealed that something in the old continuity could not survive untouched. Classical physics predicted an absurd overflow of energy at very high frequencies, a result so wild it did not merely miss the data, it threatened the sanity of the entire framework. Planck repaired the problem by proposing that energy exchange does not happen in an endlessly smooth flow. It happens in steps. At first, that was not yet a declaration that light itself comes in packets. It was more like a controlled emergency repair, a way of saving the measured spectrum from catastrophe. But once that idea entered physics, the old confidence in perfect continuity had been wounded. Then Einstein did what made the whole story irreversible. He went further than Planck. He did not merely quantize the exchange process inside matter. He proposed that light itself behaves, in some circumstances, as though it comes in discrete quanta. That was the dangerous leap. It was dangerous because it seemed to threaten everything wave optics had won. It seemed to pull against interference, against diffraction, against Maxwell. And yet Einstein saw that if the energy of light comes in packets, whose size depends on frequency, then a whole class of otherwise puzzling results begins to make sense. The photoelectric effect was the first great battleground. Shine light on a metal. Electrons are emitted, but the details refuse to fit the classical wave picture. There is a threshold frequency below which nothing happens, no matter how bright the light is. Increasing intensity increases the number of emitted electrons, but not the maximum energy of each one. And the electrons appear almost immediately when the frequency is high enough, rather than waiting to slowly accumulate energy from a weak, continuous wave. Einstein's light quantum idea explains all of this with extraordinary clarity. Each electron receives energy in one discrete transaction. If the quantum is too weak, the electron cannot escape. If it is strong enough, escape happens at once. Then came Millikan, and with him one of the most elegant ironies in modern science. Millikan did not approach Einstein's idea as a believer. He approached it as a skeptic, with the disciplined suspicion of an experimentalist who wanted the numbers to speak more loudly than the theory's charm. And the numbers did speak. They arranged themselves into a clean, straight line when the stopping voltage was plotted against the frequency of the incoming light. Again and again, with real metals and careful measurements, the relation held. Millikan confirmed Einstein's equation even while remaining uneasy about Einstein's interpretation. And that mattered deeply, because science is not about loving an idea. It is about what remains standing after measurement has done its work. Still, one refuge remained for the defenders of classical continuity. They could still say, perhaps the discreteness belongs only to matter. Perhaps electrons respond in jumps, while light itself remains fundamentally wave-like. Then Compton's scattering arrived and narrowed that refuge almost to nothing. Now light did not merely seem to transfer energy in packets. It behaved like something that also carried momentum in a collision. X-rays struck electrons and emerged at new angles with longer wavelengths, exactly as one would expect if a light quantum had collided with an electron, given up part of its energy and momentum, and recoiled. That was no longer easy to dismiss as a special quirk of matter. The light itself entered the encounter carrying a directional, transferable impulse. At that point, the particle-like description of light stopped being optional in any serious sense. And yet the story did not end there either. Because if we had stopped at that moment and declared triumphantly that light is just a tiny classical bullet after all, the rest of optics would have risen up and objected. Interference would object. Diffraction would object. The single photon double-slit experiment would object most of all. Send photons one at a time through a double slit, and each detection is local. Yes, a single click, a single event, but over time those clicks build an interference pattern. That means the photon is not a tiny classical marble choosing one slit in the old ordinary way. Something wave-like still governs the distribution of outcomes. So quantum theory had to do something deeper. It had to redefine what we even mean by a particle. And that is where the modern answer finally comes into focus. The most mature picture is not that light is fundamentally a little object flying through empty space. The most mature picture is that the electromagnetic field is fundamental. Maxwell's field does not disappear. It survives. It fills space. It propagates in ways that naturally account for interference and diffraction. What changes in quantum theory is that the allowed excitations of that field are not continuous. They are quantized. A photon is one such excitation, not a tiny pebble, not a miniature billiard ball, not a secret classical corpuscle disguised in modern language. A photon is the smallest transferable excitation of the electromagnetic field. That is what physicists really mean. And now, finally, we can answer the question with the clarity it deserved from the beginning. We believe light is particle-like because certain experiments force us to assign to it discrete packets of energy and momentum. We believe this because the photoelectric effect shows that light transfers energy in all-or-nothing encounters tied to frequency. We believe this because Millikan's measurements confirmed that relation with extraordinary precision. We believe this because Compton scattering shows that light's quanta carry momentum and behave in collisions like discrete participants. We believe this because detectors register localized events, one click at a time, not infinitely divisible smears of energy. We believe this because modern quantum optics, including single photon interference and anti-bunching, reveals a structure that classical wave language alone cannot capture. But we do not mean that light is made of tiny classical pellets. That is the crucial correction. When physicists say light is a particle, the phrase is shorthand, useful shorthand, but shorthand nonetheless. What they mean is that light comes in quanta. These quanta carry definite energy and momentum. They are exchanged in discrete events. They are detected locally. And the best complete description of them is not classical mechanics, but the quantum theory of the electromagnetic field. Waves won early because they explained so much, and because Maxwell gave them profound mathematical legitimacy. Blackbody radiation cracked the old assumption of continuity. Einstein extended that crack into a bold new picture of light quanta. Millikan tested that picture and confirmed its numerical structure. Compton showed that the quanta also carry momentum in collisions. Quantum theory then taught us that the word particle itself had to be reformed. What remains is not a return to Newton, but the birth of the photon. There is a larger philosophical lesson here, and it reaches far beyond light. Nature has no obligation to match the intuition we built from stones, waves on water, arrows in flight, or objects we can hold in our hands. Those intuitions are precious, but they are local. They were shaped by medium-sized life in a narrow slice of the universe. Physics becomes great precisely when it refuses to worship those intuitions as final truth. Instead, it does something braver. It follows mathematics, where mathematics is honest. Then it asks experiment to judge. That is the real rhythm of this story. First came the equations that classical physics loved. Then came the cracks those equations could not mend. Then came new mathematical ideas, strange and unsettling. And finally, experiment ruled on which ideas nature would keep. That is why this whole journey is so beautiful, not because it leads to a strange slogan, but because it shows science behaving at its most noble. No attachment to comfort, no worship of familiarity, no loyalty to a picture once measurement has outgrown it, only the long, patient correction of human imagination by the world itself. And perhaps that is the deepest reason this question still matters. Light is one of the most familiar things in our lives. We wake to it, we see by it, we measure the world through it. And yet when we ask what it really is, the answer carries us all the way to the frontier where common sense ends and physics begins. That frontier is not cold, it is not hostile. It is simply more subtle than the mind first expects. The deeper we look, the less nature resembles our common sense categories, and the more it rewards mathematical honesty. So this, at last, is the cleanest possible answer. We believe light is a particle-like entity because experiment forces us to treat it as carrying discrete quanta of energy and momentum. We do not mean tiny classical pellets. We mean photons, quantized excitations of the electromagnetic field. Thanks for watching, and until next time, goodbye.